All right, so we're going to do question number 6 now. It says, how many different photons from different frequencies or wavelengths for that matter, can be emitted as a hydrogen atom in the third excited state, which is of course n equals 3, directly or indirectly goes to the ground state, and then it says what are the wavelengths. Okay, so really the wavelengths are the challenging part. All right, so for the first part of this question, really, I've drawn a diagram. It's not very clear, but the outer circle represents n equals 3. The next circle is n equals 2, and then the inner one is n equals 1, right? The ground state, the n equals 1. So really what's going on here is you can have an electron go directly from the n equals 3, so I've written it over here, n equals 3 to n equals 1. So there's one photon. N equals 3 to n equals 2, that's going to be a second photon, and then n equals 2 to n equals 1. Remember, the photons can't stay in any of these excited states, whether it's n equals 3 or n equals 2 or anything higher. They eventually will go to the ground state because the higher states are unstable. They can't stay there very long. Anyhow, so there's 3. So that answers the first part of this question. So the second part is, like I said, a little bit more complicated. We're going to use this equation. Of course, this is the energy of at any state n. N always has to be a whole number, and so it's equal to 13.6 electron volts. And where does that come from, by the way? The 13.6 electron volts would be the energy to go from the ground state, which of course is the energy is equal to 0 in the ground state, to escape the hydrogen atom, right? So that's where the 13.6 comes from. Anyhow, that's equal to the product of 1 minus 1 divided by n squared. And so again, n is just a number, right? Those are the quantum levels, right? So n equals 1, for example, of course, then n, yeah. All right, anyhow, you get the idea. So let's figure out the energy, right? So it's going to be the energy in the third excited state, which is, of course, is our highest energy, would be 13.6 electron volts. It's just easier to use electron volts rather than use joules here. But you could do it with joules as well. Anyhow, it's going to be 1 minus 1 over, since it's n equals 3, it would be 3 squared. And so that comes out to be 12.09 electron volts. What about the next, n equals 2 state, right? So the n equals 2 state, which of course is a lower energy than n equals 3, would be, of course, the exact same equation, 13.6 electron volts, 1 minus the quantity 1 over, and since n equals 2, it would be 1 over 2 squared. All right, and so when we do that, the energy is 10.2. All right, so and then of course let's do the energy for, just to prove that the energy in the ground state is 0. All right, so I'm going to write that. So it's equal to 13.6. That's decimal point, supposed to be, EV, and it's going to be 1 minus, see, this is where it goes to 0, right? 1 minus 1 over 1 squared, which of course is still 1, and so 1 minus 1 gives us, of course, 0. So that's where the 0 energy comes from. All right, let's continue. All right, so the the basic idea, now that we have the energies in the n equals 3 state and the n equals 2 state, we can use the Bohr model of the hydrogen atom, which says the energy of a photon that goes from the n equals 3 to the n equals 2 is just the difference in the energies, right? That will be the energy of that photon, and then once we have that, we can turn it into what the wavelength is, and of course, that'll also give us what the color is. So remember, E3 was 12.09 electron volts, of course, minus E2, which was 10.2 electron volts. So I just factored out the electron volts. So the difference between these two is 1.89 electron volts. All right. So then we're gonna calculate what frequency this is. All right. So the next one is E, or another one. It's not really just the next. It's the next one we're going to do is the energy in the third state to the energy in the first state, right? So going from n equals 3 to n equals 1, it's going to be, remember, it's the difference in the energy level, so it's E3, E3 to E1, so it's going to be 12.09 minus 0, and of course both of those are in electron volts, and so the answer comes out to be 12.09 electron volts. Sorry, that's supposed to be electron volts. All right, and then the last one that we have to do, the third photon, is going to, it's when the electron goes from the n equals 2 state to the n equals 1 state. So the n equals 2 state is, the energy is 10.2. The energy in the ground state is 0. So it's the difference, of course, is just 10.2. So we have to there's a photon related to this energy, the 1.89, right? There's a photon related to this energy, the 12.09. And then this energy as well, 10.2 electron volts. And so the basic idea is really simple. So here, let me kind of move this off. We just have to remember these three numbers, and then the photon, so that this is just whatever that photon will be, is, remember that constant that we used before, that 1240, and of course the units are nanometers times electron volts, right? And if we divide it by the energy, that's supposed to be an E, the energy in electron volts, then the electron volts will cancel, and that'll give us an answer to the three of these, right? That this one again, remember that's the energy of that photon, that's the energy of another photon, and that's the energy of the last photon. All right, so each time we're going to use this equation, and we'll get the wavelengths. All right, this is a little bit harder problem, but we can tackle this. All right, so I've set up the first one here. So the wavelength lambda of when the electron goes from the n equals 3 to the n equals 2 state, that's what this subscript is really meaning. So lambda 3 to 2 is the 1240 nanometers times electron volts. Those are the units of that, divided by, well, what was the difference in energy levels when the electron went from n equals 3 to n equals 2? It was 1.89 electron volts. Remember, you took the difference between the energy in the n equals 3 state and the energy in the n equals 2 state. So the difference gave us this, and so that gives us a 656.5 nanometer. Notice, of course, the electron volts cancel. Right, there's the electron volts canceling, and so that'll give us an answer in nanometers, which is convenient because that's certainly within the visible part of the spectrum. Actually, that's the Balmer series. That's part of the Balmer series, and that's the red photon that is very easily visible. All right, the next one is n equals 3 to n equals 2, n equals 3 to n equals 1, and of course we had 12.09 electron volts. That's this one that we're talking about. And of course, again, you take this constant, the 12.2, 1,240 nanometers times electron volts. The electron volts cancel, right? So that's cancels this, and so this will give us an answer and so you just divide, right? It's just a division. 1240 divided by 12.09 gives us, let's see, what does that come out to be? Oh yeah, that is 102 point, so that's 102.6 nanometers. Recall, of course, visible light is from 400 nanometers to 700 nanometers, right? 400 is the bluest light, and so this is less than that, right? So this is less than 400 nanometers, so this is definitely not in the visible part of the spectrum. In fact, this is in the ultraviolet range, right? So we know that this is an ultraviolet photon, and in fact, if you look if you look this up, it turns out that this is part of the Lyman series. Lyman series. There's the ones when you go from n equals some higher number than 2, so n equals 4 to n equals 2, n equals 3 to n equals 2, n equals 5 to n equals 2. Those are the Balmer series. So this is just this top one here is the red one, and then n equals some higher number than 1 to down to n equals 1. That's called the Lyman series. There's another series, by the way, called the Paschen series. Paschen. I forget how you pronounce that guy's name. Anyhow, let's do. This is the Lyman beta photon. That's just what it's called, and lambda. So let's go lambda 2 to 1. All right. So this is the transition from 2 to 1, and then of course we already have what the energy is for that. It's 10.2. So this is just 1240. Divided by 10.2, and of course this is electron volts, this is nanometers times electron volts, right? And of course the electron volts cancel, and this number comes out to be 121.6, is that right? Yeah, 121.6, and so this is also in the ultraviolet. This is a that's supposed to be a UV ray, and that's actually one of the Lyman series as well. Remember, the Lyman is when you're going from a higher number to down to the ground state. So these are just the people that discovered this particular pattern. Anyhow, so this is actually the Lyman alpha. Right, and so this is the Lyman alpha, and so all right, so that is problem number what one was this? So 6, yeah. All right, so let's come on. Where's my? All right, I've set up some of problem number 7. All right, so let me read it. It says a distant galaxy is receding from Earth with a with a radial velocity of 3,000 kilometers per second. So by the way, that means it's moving, so if it's moving away from us, that means it's red shifted. Okay, we really need to remember to use that terminology when something's moving away. Remember, it's blue shifted if the objects are moving towards each other. All right, anyhow, let me continue with the problem. At what wavelength would its Lyman alpha line, right, which we just talked about in the last problem, the Lyman alpha line be received by a detector above Earth's atmosphere? So in other words, what's the wavelength? So lambda is equal to what? And of course, the Lyman alpha line, and I'll write it like this: Lyman. So the Lyman alpha line, this is the rest wavelength. If the two, if the two objects are at rest. In other words, if you take some hydrogen, you heat it up, and you look at it in the laboratory, the Lyman alpha line turns out to be, let me write this down. Let's see, what is it? 1 121.6 electron, 121.6 nanometers, right? And so so we use this equation, right? This is the Doppler shift equation right here. And we just put in all those numbers, and we'll calculate what lambda is, right? So we